Hello, and once again, welcome to the last class on stereoisomerism. Rudra, have you revised what we did?
Yes, sir.
Good. Today, we are supposed to uh, complete the remaining portion. That is, let me write down substituted. Can you see my screen?
Yes, sir.
Can you see my screen, Rudra?
Yes, sir.
Rudra,
Yes, sir.
Rudra,
Yes, sir.
can you see my screen?
Yes, sir.
Okay. ଆଉ କୁଆଡେ ଶୋଇପଡୁଥିଲ କି?
ନାଇଁ ସାର୍ କହୁଥିଲି।
ଶୁଭୁନଥିଲା, ଆଚ୍ଛା ହଉ। Now, substituted cyclohexanes, number 2 is the wedding ceremony today. Configuration versus conformation. And more on substituted rings. Same configuration versus conformation. Now, yesterday, Rudra, we had seen in cyclohexane, there are two rapidly interconverting chair forms. One chair form is converted to the other chair via the half chair form and the skew board form. But between the two skew boards, which are mirror images, comes which form?
Sir?
Between the two skew board forms, which transition state comes?
Boat form.
Boat form.
Precisely, Miss Tripathi is correct. You are late. But the rapid flipping between the two chair forms can be lowered down or can be completely stopped at minus 78 degrees Celsius, where you can see the axial and equatorial hydrogens are distinguished. By some chemical method, we can find the difference. But at room temperature, they give an average effect because of the rapid flipping. Now, we shall be looking to the substituted cyclohexane. First, monosubstituted. Now, as a representative, we'll take methyl cyclohexane to understand. You know, there are two conformational isomer or conformers or rotamers. One is where the group, say methyl or alkyl, whatever, group is occupying in the equatorial position, and that is called the E isomer, equatorial isomer. But the rapid flipping into the other chair form will make it the same, will now be lifted up, will be occupying the axial R. So this is called the A isomer. These are simply conformational isomers or conformers or rotamers. These are not optical isomers because there is no plane of symmetry. There is no chiral center anywhere or chiral axis. Nothing is there. So these are, rotamers. Because the plane of symmetry passes between carbon number 1 and 4, So it is symmetrical molecule. And for a layman point of view, this carbon is bonded to, two identical groups on either side. This part and this part is exactly identical. So this cannot be called a chiral center. And also you can justify by finding a plane of symmetry. And interestingly, the axial isomer, A isomer, is unstable. More stable. So in the room temperature, nearly 95% you will find the E isomer and 5% of A isomer. Why it is more stable? Because now it is better to say why this is less stable. Now this axial isomer suffers to Gauss-butane type of interaction. Here this is trans to this is trans to this, but this is Gauss to this. So the model looks like as if they're 90-degree, but they're actually Gauss 60-degree apart. And also this is also Gauss to this bond. I'm sorry, this bond. Oh, I'm so sorry. This bond. So it looks like as if they're 90-degree, but actually, I think I will refrain today myself of showing you models, but I may, because I'm in a hurry to finish by 7:30. I think I can do it. We can do it together. Hello and welcome those watching from the YouTube. This is the last class on a very important topic, which I wanted to make it a public video. Interesting thing, let me share with you a secret, that by doing so I have gained by about maybe 10 subscribers. So that's enough. I'm not pushing myself. I'm getting, rather I am getting encouragement, harnessing that into some useful work. Hello, Mr. Tripathi, welcome. Now, you know that the Gauss form is less stable than the anti by 0.9 kilocalories per mole. So there are two Gauss-butane type of interaction. So this is anti form. So the axial is more stable than equatorial by 1.8 kilocalories per mole. Because the axial isomer has two Gauss-butane type of interaction. I used to write ZBI. And equatorial isomer has no such interaction, but the one which is in the axial position, this has this one lying 60-degree apart. In the diagram, it doesn't look like. And this also bond also 60-degree apart. So some little bit steric, strain is there. As you know, although both are staggered, format every two adjacent carbon atoms you look, you will find staggered in all the chair forms, but it has two GBIs in axial, no GBI in equatorial. So the energy difference 1.8 makes the equilibrium constant such that 95% of the molecules at room temperature remains in the equatorial form. Coming to disubstituted cyclohexanes, very interesting. Very, very interesting. Here we shall be taking off 1, 2, 1, 3 and 1, 4. Because these things will be required for our GCOC. When we study mechanism in cyclohexane, substituted cyclohexane, if it is in the equatorial position, then the new group will occupy the axial position if it is a SN2 process. So, and sometimes SN2 will not happen because of steric congestion. That things will be very easy at that point of time. So let's first take up 1,2 disubstituted. For a representative molecule, we will take 1,2 dimethyl cyclohexane. Here you will encounter with the geometrical isomers as well as enantiomers, as well as conformational rotamers.
Dimethyl cyclic.
Disubstituted. I'm writing disubstituted in general. 1,2. We'll be taking 1,2.
Okay, sir. Okay, sir. Yes, sir.
So in 1,2, you have two GIs. One is cis, the other one is trans. In a layman's point of view, when you are asked to study very fast, then you make a planar model like this and study what should be the state. 90% case you will not fail. Your judgment will be correct, but 10% there will be a possibility that you may fail in some critical questions because this is not a planar model. So in planar model, when you write, I'm just showing the methyl remaining opposite. So this is trans. This is just like, tartaric acid. You say this as a trans, but this is, we have to immediately think of the active tartaric acid, DL tartaric acid. It has got another, because there is no plane of symmetry, no center of symmetry. Center of symmetry would have happened had there been a 1,4 positioning. It is 1,2. So the center is here. You have to, draw as many, bonds, straight lines as possible. Infinite number of straight lines. You will find identical groups will be touching at equal distances. So the question of point of symmetry doesn't arise. So this is a disymmetric molecule and it has got a mirror image. So you will be writing like this. This is HCH3. They are non-superimposable. So this is a layman point of view. You will be giving a DL pair. So the trans exists. Trans, when you say trans, it means it is a geometrical isomer relative to cis. But within trans, there are two enantiomers. Trans exists as a DL pair. But when we study conformation together, you will find there will be two pairs of enantiomers. It's not only one pair as predicted from the planar model. Two pairs of enantiomers. And every, say, trans will remain maybe 99% in one of the conformations, one of the rotamers, which is again 50-50 if 99% will be there for one particular conformation. I repeat, conformation. The other one is extremely unstable. But the extreme unstable one, maybe 1%, is also optically active, dissymmetric. But in planar model, we will predict only one DL pair. But in actual sense, there are two pairs of enantiomer. But I'll show you. So in this cis, this is trans. This is cis. Obviously, people will call there is a plane of symmetry. Methyl will remain on the same side, whether up or down doesn't matter. So there is a plane of symmetry, people will say, so it is meso, they will say. But you will see what will happen in the real case, in the real situation. You will find that it is not meso. What discovery you will make, I will tell you, just you hold on here. When you study the real three-dimensional puckered chair form and flip into the other rotamer, you will find. So let's take up first the trans 1. Trans 1, 2. Trans 1, 2 has two rotamers. This is a GI, but it has got two rotamers or conformers. One is EE, di-equatorial, where both the groups will remain in the equatorial position, called di-equatorial or EE. Or if you flip it, it will become AA. Goes without saying, diaxial. But you will find axial has so much of difficulty, stability difficulty. One axial will suffer 2 GBIs. So 2 axials will suffer 4 GBIs, 4 into 0.9, 3.6. And in case of di-equatorial, only the substituents are having Gauss only one between them. The two, one is slanting up, the other one is slanting down. That alternatively happens. The opposite side. That is the opposite side. That is why geometrically it is called trans. Diaxial is understandable. Di-equatorial also remains in the opposite side. You will see. One is slanting upwards, the other one is slanting downwards. But you will find that only has 1 GBI between them. So 0.9. So 3.6 minus 0.9, 2.7 kilocalories per mole. EE isomer is more stable. EE rotamer is more stable than EE rotamer. As a result, you will find 99% of the molecules will remain in the di-equatorial EE, not AA. I am just showing you in case of 1, 2, supposing this is 1, this looks like as if they are close, but one is slanting up, the other one is slanting down. One is up, and the other side it is slanting down, like this. So they are apart from each other. You know, distance wise, you will find in compared to the cis, the two substituents, say methyl, R or R, whatever. So this is EE. And once you know, these rotamers, they're rapidly interconverting. Unlike it is the case of very strained molecules. I showed you one cycloalkene where you got the conformational enantiotropism and antiotropism, cyclic compound. A cyclic compound, you know, exactly not acyclic, biphenyl, tetra substituted biphenyls, both are rings, but the rotation is about one single bond. But cyclooctene, the example that I gave you, that, you know, transform, that, you know, you have to rotate two single bonds simultaneously to get, that is very difficult. The energy barrier is quite high. So they remain independently. They can be separable. But these, you can't separate them. In cyclohexane disubstituted compounds, you can't separate them. They always will remain together. But the good part is that it's 99%. It is once you convert to the other chair form. So, and now this becomes axial in this, you know, 1, 2, 3, 4, 5, 6. This one has come down 1, 2, 3, 4, 5, 6. So this becomes AA and this is EE. EE has, I write, with respect to no interaction, I write 4 into 0.9. Sorry. Sorry. Between these two R, there is only one Gauss-Butane type of interaction. So the interaction energy, we call it interaction energy compared to no GBI, when all trans and T. Interaction energy here in the di-equatorial trans is 0.9. But here, this one is the interaction energy is 4 into 0.9, 3.6. So the difference between these rotamers, so EE is more stable than AA by 2.7 kilocalories per mole. So nearly 99% of the molecules remain in the EE form and only 1% remains in the AA form. It remains. And interestingly, both the enantiomers, sorry, I'm so sorry. Both the rotamers, both the rotamers are dissymmetric. You won't find any of the three elements of symmetry. And I'm not spending time. Both the rotamers are dissymmetric. Had I got some more time, I would have, cared to open the model. But you guys are so good. There is no point. Maybe sometime when we will study the mechanism of cyclohexane, I might so. But both rotamers are dissymmetric and exist as DL pair each. So there are how many optical isomers for the trans compound? Trans 1, 2 disubstituted.
Sir, two.
4. There will be 4. There will be 4.
Okay, sir, four.
Yes. EE has 2, AA has 2. But they are intercompatible. We can't separate them. The D and L of EE cannot be separable. The D and L of AA cannot be separable. So you have to be there. It's not possible to resolve. Yeah. One thing I have to discuss in some other day. That is, today is not possible. The resolution of a racemic mixture. Some other day, but today I will declare the end of our program, no doubt, because I had a plan for 7 lecture program that is ending today. Both the rotamers are dissymmetric, exist as DL pairs. Okay. Now coming to so the net result is racemic mixture. You don't find no optical activity. It's not due to meso, but due to external compensation DNL. No optical activity because they cancel each other. The EEDL, they cancel. AADL, they cancel. So net activity is 0. But it exists as a DL pair. Coming to cis. Cis has 2 rotamers, AE, and if you flip it, it will be EA in the same sequence. These are same energy, equal energy, because each of them has only 2 GBIs for the axial one. Equatorial is lying flat, so it doesn't enter into any Gauss-butane type of interaction. Now I'm showing, supposing in this one is axial and this one is equatorial. They are closer than the di-equatorial trans. I tell you, had I shown you the model, you would have seen the distance is closer here. A, this is R. This is E. EA. This is in the same sequence. I am numbering 1, 2, 3, 4, 5, 6. So we will call it AE. But if we flip it to the other chair form, which is rapidly happening, because the barrier to this flipping, all these flipping process is not much, unless some very strong bulky group is there, I'll tell you that. Where this one comes here, this, this goes up, 2 is here. Now, where is 1? 1 is here, 1. So the 1 goes to the equatorial position and 2 goes to the axial position. So in the same sequence, this is EA, equal energy. a big problem. The big problem is that in the planar model, you say it is a mesoform. But actually, it is not a mesoform. It is active. There is no and it is a disymmetric. Each one is a disymmetric molecule. But interestingly, the two are related as mirror images. They too are related in mirror images. Had I, got the model, then I would have rotated 120 degree about a vertical axis and showed that the two are related as mirror images. So always 50%, 50% remains. So optically inactive, but not due to meso, but due to external compensation. So each one is disymmetric, but EA and AE are mirror images, are enantiomers. So we can't separate because it's rapid flipping process. It will remain together in equilibrium. So it is inactive. So also the other in the diequatorial and diaxial trans, that also was optically inactive, but they were disymmetric. This is disymmetric. That is also, but this goes in total contradiction to the planar model, which says it is meso. And if you are writing an answer in an advanced level question in IIT advanced level, the professor will never set a question indicating that this equally stable cis AE and EA, it is a mesoform and therefore it is optically inactive. No, it is optically active, each one. Maybe at lower cryogenic study will prove the flipping process can be stopped and you may be able to very carefully, you can remove them at very sub-zero condition. But at room temperature, no, it's not possible. But they is optically active. Now, coming to the 1-3, now we'll be studying how we were studying. The first one, I dye substituted 1-2 without any AB. So this is then 1-3. Oh, no. Now who can tell me? Cis and trans, same 1-2, are diastereomers. They are geometrical isomers. Hence, different physical properties. Who can tell me which you can separate them? Supposing in one synthetic process, you get a mixture of cis and trans of 1,2-dimethyl cyclohexane. The trans will be containing 99% of the EE and 1% of AA, while the cis will be containing 50-50. I didn't write 50 of this and 50 of that. It is understood. Enantiomers, but optically inactive, but the compound is optically inactive due to internal compensation, not due to is inactive as a racemic mixture. It is a racemic mixture, inseparable racemic mixture at room temperature. That is important. You can't separate them. Always you get null. I mean, the optical rotation is 0. Inseparable racemic mixture at room temperature. Cis and trans are diastereomers and hence can have different physical properties, which you know and can be separated. Who can tell me here? Let me write down interaction energy is equal to only for one axial, either here or here, doesn't matter. In the 1, it was axial. Now it is 2, it is axial. So it doesn't matter. Only one axial is 2. 9 into point is 1.8. Right? So tell me, between the more stable EE form of trans and equally stable AE and EA of cis, what is the energy difference? How much more stable is the trans isomer than the cis isomer?
Like 0.9 kilocalorie.
Obviously, because diequatorial is only having 0.9 between them, and this is 1.8. So more stable by 1 point, that is only 0.9. But even then, they are diastereomers. They can be separated. Their physical properties are different. Now, let me check whether this is going okay or not. It's okay, but 1.8. No. Something is going wrong. That's why I was really thinking. The interaction energy 1 to trans is 99.1%, 2.7, that is okay. And cis has interaction energy of, oh, this is 1.8, okay. Yeah, but the trans isomer is more stable than the equally stable form of cis isomer by 1.8. How? Because here we have not written the interaction energy anywhere. Because one axial means there will be two GBIs. Have you written? No. So I think it's not correct. So the interaction energy here, each one is chiral and two are mirror images of each other. Interaction energy see, this one has this bond and this bond is Gauss, this bond and this bond is Gauss. So there will be two GBIs for each axial substituent. So interaction energy is 1.8. Now see, in the diequatorial, the interaction energy is 3.6, and diequatorial it is only 0.9, and diaxial is 3.6, and diequatorial is between them is 0.9. So 3.6 minus 0.9 is how much? Is it not 2.7?
Yes, sir.
So there is a mistake here. It is the 1.8 kilocalories per mole for the axial substituent. So here 2.7 and this is point, so more stable by 0.9. Now coming to, let us come to the 1,3. Hello and welcome. Those who are watching now, if you guys are watching, I asked someone to just say hi to me if you are watching from the YouTube. Okay. Then coming to 1,3, disubstituted cyclohexane. Here also there are two GIs, cis and trans. I deliberately chose to write cis first, trans second. There, trans first, cis second, because the principle of rotamers are same, EEAA, where the trans rotamers. Here in 1,3, it will be cis, they will be closer to each other. And the AE and EA equally stable, AE and EA, that was cis for 1,2, but 1,3 it will be trans, they will be farther from each other. So you can visualize in the model. So let us talk about cis. It has got two rotamers. I don't think I have to take one more class. One is EE, is AA. Obviously, EE is more stable than AA. Now I'm talking of 1, 3. Supposing this is 1. Now let's say start from equatorial. R is here, 1, 2, and 3. This R is also here. And if you flip it to the other one, supposing this is 1, 1 has gone up, 2 is here, 3 is here now. 1 will be having axial, 3 will be having axial. And there will be, now I was hinting yesterday, I was last class, there will be huge 1,3 diaxial interaction. That is a steric interaction. That will make it very, very less stable. The interaction energy difference, GBI is 4, 3.6. In addition to that, 1,3 diaxial, not 1,4, diaxial flat pole interaction that is in the board form. 1,3 diaxial interaction, that corresponds to, if the total is 5.5, यार contribution कितना होगा?
1.9.
Huh?
1.9.
1.9 comes from the huge diaxial, 1,3 diaxial interaction. They remain on the same side, either both up or both down. So this is EE isomer, this is AA. We are talking of not trans, cis. And this is 0 GBI. So EE is far stable than the AA. So more than 99.9, maybe nearly 100% molecules remain in this EE form. 5.5 is too high, nearly 100%. It's not exactly 100%. But interestingly, both are here meso. There is a plane of symmetry passing through 2 and 5. You cannot visualize, you can visualize here. Same thing happens there also, 2, 3, 4, 5. So you can visualize a plane, not an axis. Plane passing through carbon number 2 and 5 will both prove to be plane of symmetry for EE as well as AA isomer. Both have sigma plane, that is plane of symmetry, passing through C2 and C5, and hence mesoforms. I don't know if we, consider, in many literature, you'll find the analysis has been done in the planar model, and they call it pseudo-planar model. So 1, 3, supposing this is 1, this is 3. And we are talking about cis. Cis means on the same side. Yeah. Yeah. Because if it will be symmetrical hexagon, very symmetrical hexagon. So if one is here, the other one is here on the same side, then it looks like as if there is a plane of symmetry. So this reflects with this, and this bond reflects with this bond. This bond reflects with this bond. This bond reflects with this bond. Yes, there is a plane of symmetry. Also, that can be visualized from the planar model. This is a planar model, which is not correct. So in the 3D chair form also, you can visualize both are inactive. But the percentage of diequatorial is nearly 100% because of huge interaction energy difference. Coming to the trans isomer, or AB, we're writing A, B. not AB. It's nothing. It's nothing. Not 1, 2. Trans 1, 3. It has got two rotamers. Rotamers which cannot be separated. A, AE, BEA in the same sequence. But interestingly, you will find both are identical. Both are by manipulating the two, by after flipping, by manipulating one, you will exactly superimpose with the first one. They are one and the same. Unlike the case of enantiomers in case of 1, 2 cis, but this is 1, 3 trans. It's identical. And it is dissymmetric. Therefore, when you synthesize such a trans 1, 3 disubstituted cyclohexane, you will get a mixture of cis and trans. Separate the trans, you will find you will be having two enantiomers which are not rotamers. Two enantiomers which are not rotamers. Each enantiomer is flipping between its AEA which are identical. So, interestingly, students fail to understand this trans 1, 3 that exists as a separable DL pair. They confuse because each enantiomer has two rotamers, AE and EA, which are identical. But during any synthesis of an optically active compound, you get always enantiomers unless you have a very sophisticated technique which is called asymmetric synthesis. I think I had a plan sometime after. We'll talk about asymmetric synthesis where you can tilt the product in favor of either R or S. I mean, in some D or L, maybe 90% D, 10% L, or maybe nearly 100% D. So there is some technique which you follow so that you induce a particular configuration in the chiral center of your required target molecule. It's called asymmetric synthesis, which we will not discuss here. So these two, let me show you. But by showing you cannot visualize unless you have a model. But since I'm saying, the book is saying, you believe it now. You understand, you are so intelligent guys. So if one is, oh my God. Supposing this is R and this is the third position. This is E. This E, this E. This is up. This is down. This is up. This has to be down. Oh, looking like axial. Oh my God. Axial will be up. This is R. This is E. This is A. And if you flip to the other 1, 3, this will go down. And 1, 2, 3 in the same sequence. 1 is here, 2, 3. So here this will be equatorial and this will be axial. So this is equatorial, this is axial. This is, call it AE, this is EA. Here, AE is equal to EA. Both rotamers are identical. Hence, during the synthesis of such compound, when we get and robots are identical and is dissymmetric. Is dissymmetric. That you have to mention. Is dissymmetric. No, unlike the EE and AA of cis, which was having a plane of symmetry in both. Although AA was almost a non-entity because the interaction energy is 5.5, but they are meso but this is active. There is no elements of symmetry to make it active. This is dissymmetric, but you can separate them. If you have a mixture of the two of such compound, if hence during the synthesis of such compound, we get a DL pair, a racemate, we can separate them. As each enantiomer has two identical, they are flipping. But what happens? Nothing is happening. It's not even giving enantiomer. It is giving itself as two identical rotamers. So we say the 1,3, this is trans, exist as a separable DL pair. Separable DL pair. That doesn't mean that it is a racemic mixture. You may get 100% D. Who knows? If you following the asymmetric synthesis method, you can get 100% D or 100% L. But usually, in normal procedure, we get a DL pair. So you can separate them by resolution of the subject I've not yet discussed. And I just sounded you. For functional groups like carboxylic acid, alcohol, phenol, you can convert it to diastereomer by reacting with a pure other compound. It's complementary compound to form an ester or amide or whatever. And then finally separating the diastereomers and then hydrolyzing, getting back a D and L separately of the original mixture. So here, 1,3 trans exists as a dissymmetric molecule, either D, you can get 100% D, 100% L, but usually DL pair, you can separate them. You understand?
Yes, sir.
And, you know, this has also interaction energy of, because the one which is, axial will suffer from only 2 GBIs. In the case of the 1,3 diaxial interaction is very, very small because hydrogen is there. So there can be a little, so it might be little more than 1.8. So it is approximately 1.8. I'm doing this to compare between cis and trans. So as already told you, the cis and trans are diastereomers, can be separated very easily. But tell me, between cis and trans, equally stable, this is 50-50. Not 50-50. we don't write 50-50. This is 100% one. This is one and the same. That's the beauty. So stable, the A form, which is 1.8 approximately. And in the cis category, we have the EE, which is 0. So it is more stable by 1.8. The cis is more stable than trans. In this case, cis is more stable than trans by 1.8. Trans has a interaction energy of 1.8. Cis, the stable rotamer EE form of cis, has 0 interaction energy, and therefore the abundance in the if you prepare such compound, you get mixture of cis and trans. You can first easily separate them. Then looking to the trans, if you look to trans, the trans will remain as a DL pair. Then you can also separate them, because each of the D and L, they exist rapidly flipping identical forms, so they can be separated easily. There is no conformational enantiotropism here, so we can mention here, in this case, identical, no conformational enantiotropism, as we found in the case of cis 1,2. In trans 1,3, there is no conformational enantiotropism. The conformers, rotamers, are not enantiomers. They are one and the same. Now, coming to 1,4. So this has also two GIs, but very similar to 1,2, cis and trans, trans and cis, because it is similar to 1 and 2, 1, 2, sorry. So let us first take the trans 1,4. So it has got two rotamers, one EE, two AA. Obviously, in 1, 2, there was an additional 0.9 between themselves, but that will not be there because they're miles apart. So AA has, 3 point, the interaction energy is 3.6. So this is 0. So the difference is 3.6. So nearly all molecules remain in the di-equatorial form. So this is very easily, this can be shown. First, if you, this will become di-equatorial. So both have plane of symmetry passing through 1 and 4, C1 and C4. So they are meso compounds. Although AA is a misnomer, AA doesn't come. It is being less stable than the EE by 3.6 at least. So we have not included the diaxial interaction between alkyl and the third hydrogen atom. We have neglected, doesn't matter. So each one is a mesoform. And coming to the cis 1,4, AE, that has two AE and EA equally stable. Both are, also meso. Maybe because the plane of symmetry is passing through 1 and 4. So they are also meso. So the question of enantiomerism doesn't arise. But in case of trans 1,3, AE and EA, there is a dissymmetric molecule, but these are all, both cis and trans, both are symmetrical. The most stable EE form of trans has nearly 100% abundance, but here it will 50-50. But no one is optically active. So the question of saying that it is a racemate or identical doesn't come. So you can show them. If this one is, say, E, this one is E, this is A. And if we flip to the other form, which is happening, this comes down 1, 2, 3, 4. This will be this one which was equatorial will now occupy axial, and this fourth position which was axial will be equatorial. So this is supposing in the sequence 1, 2, 3, 4, 1, 2, 3, 4, we call it EA. This will be AE, also meso. And the two, this has the equally stable, no interaction. Interaction energy is 0 because both are. And forget about the di-equatorial, which is 3.6. So the most stable form of trans and the equally stable form of cis, they are different. Cis is less stable than trans. By how much? Cis is less stable because one will have at least interaction energy is 0.9 into 2 is 1.8. So the difference between cis and trans is how much? How much?
1.8.
1.8. Cis is less stable, trans. So let us write down in the other way we have been doing. But in case of 1,3, which is more stable? Out of the two diastereomers, cis and trans, which is more stable? Cis or trans? 1,3. The cis was
Cis,
EE.
sir.
Yes, yes, yes.
Cis was
Cis,
EE.
sir.
So cis was more stable than trans, hugely more stable than trans. Cis was more stable because the cis was EE. EE has interaction energy 0, but about the equally stable cis AE and EA of 1,4 and 1,2. 1,2 cis and 1,4 cis AEA. The difference is that AEA of 1,2 they are enantiomers, but they exist as an inseparable conformational enantiomers. But here there is no plane of symmetry, both are meso, but the interaction energy is 1.8 and the trans diequatorial is 0. So which is more stable here? Which is more stable?
Sir, cis.
Mr. Tripathi, which is more stable?
The trans.
Yes. But sometimes this is all about, sometimes when we study mechanism, taught butyl group in monosubstituted cyclohexane, if you have a taught butyl group, so it will not go to axial. The 5% possibility is ruled out. 100% E isomer. Because the flipping, this barrier to rotation becomes large enough for flipping. So therefore, we take, for studying anything here, this is third butyl TBU group, you take it. This is, we can keep it. Some group we are studying, supposing some SN reaction we are having here. But this one is EE, this is trans 1,4. And this is H. And the corresponding cis isomer, you cannot change this. It will always remain in the equatorial form. Accordingly, you have to change this one. So, taught butyl group, let us write out always, we will not write this. It is better to write always remains in the equatorial position. Axial, if it goes to axial, then there will be huge 1,3 diaxial interaction even with hydrogen. And moreover, the other strains will be very, very high. They always remain in the equatorial position. So I was just telling you that if you take trans compound, if you want to stop the flipping process, you do not go to cryogenic study to lower down the temperature to -70 or something. You can do manipulate a bulky group in the fourth position, which will remain always in the equatorial position. And we are interested to study the mechanism here, what is happening in the first position. And here, this is equatorial chlorine, and here it is axial chlorine. And these two geometrical isomers are trans and cis. And we are doing some reaction, say OH minus ion. So this will come in this This is Sn, so it will come in the opposite side, so it will be occupying here. So this will go, so this will occupy, the OH will occupy here, so that you get the alcohol that you get, cyclohexanol that you get will be trans. But here, it will go from upper side, and therefore chlorine will go here, it will be there, so it will be cis. Starting from trans, you are getting, then only the mechanism will be confirmed to be SN2. So all this I'm telling you because we will be studying something deep-rooted in our GCOC and mechanism part. Once you are thorough in GCOC, obviously that includes mechanism, then the study of the chemistry of the different types of compounds will be as easy as as what is the easiest thing that you can do is to sleep. Some people sleep more than 12 hours. They have a fantastic gift from Almighty. Whenever you ask them, they will sleep. Sleep. But some people are not that fortunate. They struggle very much to get a good sleep. So this is and well, any question at this stage you want to ask me? Anyone? Yes? No?
sir.
No, sir.
Because you are so good. So you are understanding whatever your teacher is saying, 101% it is going into your head, this level, not above the level. So why to ask? Now, wedding ceremony, I don't think I will start the Pandora. If you start now, it turns out to be a Pandora box. But for you, it will not be a Pandora box. Let's start the wedding ceremony. Shall we?
Yes.
Yes, sir.
Who will be from the bride side and who will be, tell me, from the groom side? बारात के साथ कौन होंगे, कौन होंगे, क्या बोलते हैं ब्राइड को हिंदी में, क्या बोलते हैं? दुल्हन. दुल्हन के साथ कौन होंगे बताओ? let me be the from the dulhan side. You guys be in the bride side because you'll dance. Oh, I can dance. Yes. You have not seen my dance. I used to dance with my granddaughter. The only granddaughter who likes to dance with me. Absolutely. Yes, I can dance. So, let us now just close. I will be back to this pseudoplanar study for other smaller membered compounds like cyclopentane substituted, cyclobutane substituted, cyclopropane substituted. There, pseudoplanar model study will not deceive you or put you in a trap as per the question. But this cyclohexane, you will fail, particularly in 1,2 cis and 1,3 trans. 1,3 trans is actually identical. It's a disymmetric molecule, exists as a separable DL pair. But cis 1,2 exists as an inseparable DL pair. The conformers are enantiomers. So why I am repeating again and again? You guys are so fantastic.
No, sir.
No. See, see the naivety. See, he's so naive. I am just telling in a sarcastic manner. She says, in a very naive way, he's answering to. Good. Hello and welcome. Guys are watching from the YouTube. Can make a hi. Just tell me a hi, sir, because I'm not a conventional teacher who needs so much of this. I'm a hi bye sir. Hi, hello. Because I am acquainted with students teaching in US soil, saying me my name, first name. So I'm habituated. Hi, Sudhanshu. That's fine. That's their culture. And our culture is something different. I'm a dodha mundugu pitiu. Kahakut dekla mane, hey, mା ଶିଖେଇଥିବ ମୁଣ୍ଡିଆ ମାର କି ମୁଣ୍ଡିଆ କାହିଁ ମାରିବ କାହିଁ ଢୋଢା ପିଟିବ ହାଇ କଲେ କଣ ହବନି and therefore our children they shy away, they just go away whenever a guest comes because there is one formality, hey mundiya mar chhadibeni se. Some people they always tell me that tame to ete katha kahucha, you what you do, I have changed, I say namaste, namaskar even to my seniors. They sometimes they after looking to my gesture, they are used to it. Or at the most you can bow down your head. Why to touch the feet of some person? The feet is the filthiest part of the body, and particularly old people, you don't touch the feet because they'll be having a lot of bacteria, because they answer the call of the first nature so many times that you will find spots of the uric acid and germs, I mean bacteria. So why to touch? So I'm telling something nonsense. But oh, sorry. Who are there? The guys who are watching, who are in the bright side. I am from the bright side. But even if I am from the bright side, I will go and join in your Bharat, and I will also dance and again come back and take the bride to the Baran Mala, and then the formality will begin, and Fere will continue. That today I think we can't go to the extent of Fere. Configuration and confirmation. Now see, it's a very simple case I will be doing. Say, I'll be taking a chiral molecule 1,2-dichloro, 1,2-diphenyl, ethane. In a simple manner, you can write down the structure like this. But just like tartaric acid, it has got 2 chiral centers and the possibility of mesoform because structurally this is symmetrical. So we can have a diastereomer which will have a plane of symmetry. It is not optically active, but mesoform will be there, no doubt. So 1,2-dichloro, 1,2-diphenyl ethane. Let's analyze the mesoform. It will have mesoform, it will have active form, DNL. One is RR, the other one is SS. Now, let us draw the Newman projection formula because all are staggered format. Now, in that, how you write, the identical pairs will remain opposite to each other. Wherever you write, then you will realize a point of symmetry or an inversion center, which by 180-degree rotation will come to a rotamer, which is not a rotamer, which is a conformation, simply a conformation where you can realize the plane of symmetry. That's the passing phase. Now they're rapidly rotating via, but it's not staying. But every moment when you analyze, 99% will remain in the staggered format. But within the staggered format, there will be 3 rotamers. Sometimes 2 are enantiomers. Sometimes 2 are identical. So even the rotamers sometimes are not considered for, and the number game. I will show you the integer type of question. How many diastereomers if you are asked, so enantiomer will not be considered. But if all are different, then you will say 3 rotamers. They are rotamers. They are not diastereomers. I'm so sorry. They are rotamers. They are one and the same, meso. I'm so sorry. But out of the 3 rotamers, 2 may be enantiomers. Now let's see what happens here. This is the perfect mesoform. Then the trick is you have to get another staggered form. You have to make 120-degree rotation, 2 times more, so that you come back to the same. If you make 3 times, then you come back to the same form. But if you make 2 times 120-degree, you are generating staggered format, but 2 other rotamers. Maybe the 2 rotamers may be identical, maybe enantiomers. Let's see. Let us keep the front one fixed. We are changing the conformation. Here lies the wedding. We have selected a particular diastereomer. There comes configuration. We have fixed the configuration. We're changing the conformation just by rotating 120-degree, so that I'm putting the front carbon atom fixed. And then same format, chlorine will come here with a 120-degree clockwise rotation. Phenyl will go here. Hydrogen will come here. And the trick is another 120. Do the same format. That is the staggered format. Now we have kept the front one fixed, pH, Cl, H, and making a clockwise rotation to the rear carbon. So phenyl will come here and hydrogen will come here and chlorine will go there. So you will find here the dipole moment for this conformer, rotamer 1, 2, 3. We will see that 2 and 3, they are energetically same. Because phenyl, they are gas, and chlorine also gas. Same is the case here. Phenyl gas, chlorine gas. So energetically 2 and 3 are same. While it has got both of them, mu is non-zero, because these polar bonds, they will have an angle of 60-degree dihedral angle. So the 2 vectors will be giving a very appreciable resultant. But the anti-form, this form, rotamer 1, we can call it anti, because we can call this Gauss. This is perfectly anti, all anti. This has no anti. Gauss form, phenyl Gauss, chlorine Gauss, and here also same. But what to find the relationship between 2 and 3? Are they identical or are they enantiomers? What do you think? Hello. First of all, tell me which is thermodynamically more stable and will be more abundant. Rotamer 1, rotamer 2, you answer in the language of rotamers 1, 2, 3. Which? Yes, Miss Tripathi?
Sir, can you repeat the question?
Question is, out of the 3 rotamers, which is most stable, and hence the mesoform of 1,2-dichloro, 1,2-diphenylethane will exist abundantly in that particular rotamer.
Sir, the first one.
The first one, precisely, Ms. Tripathi is correct. Because there is the dipolar strain is minimum, this dipolar strain is opposite is minimum. This steric strain is also minimum, they are opposite. So both the strains are minimum, and it is a staggered format. No bond opposition strain. Only there will be some steric strain will be there between phenyl and chlorine. That is unimportant, but most important is phenyl is the bulky group. Phenyl is opposite chlorine. Their polar bonds, they cancel each other, so it's a non-polar molecule. The dipole moment is 0. But these two rotamers are how they are related with each other. How the two are related with each other? Looking like as if they are same. Phenyl gas, chlorine gas. But if you try to manipulate the model, don't rotate, only manipulate the model, you will never ever superimpose. I tell you, they are enantiomers. Energetically same, but they are enantiomers. Remember, in such situation, the Gauss forms, as we say, Gauss, 2 times Gauss with respect to phenyl, Gauss with respect to chlorine, these two forms, they are enantiomers. But energy-wise, they are same. So if you are asked the question, how many conformers will be there? You will say, including enantiomers, 3. Or if you don't include enantiomers, then 2. We will see the question. Question will be accordingly framed. You must know these two, although energetically same, looking like they are superimposable, they are not. They are enantiomers. And the next question is, since the more abundant form is all anti, the first one, which has a 0 dipole moment, the net dipole moment of the mesoform is very less. You will find in the active form, where there will be no plane of symmetry, you will find that the dipole moment of the average dipole moment of all the rotamers of the active form will be much greater, because there will be no rotamer where the phenyl will remain anti and chlorine will also remain anti. So you will find that the net, the average dipole moment of mesoform is 1.27 dBi. There you'll find 2.85 dBi, which is much greater. So if you make active, supposing you write active, any active form, whether it is RR or ASS, doesn't matter. Just you make a one switch at any chiral center. Supposing I will interchange between these two and keep the rear carbon fixed, so that I will convert the mesoform into active form. Then I will start my rotation business, which is not going to change its identity. Now we are doing bond breaking and bond remaking to convert one configuration to the other. Hydrogen will come here, chlorine will go there, and the other 3 will remain HCl, pH, and here it was pH. Now see, although in this form pH comes anti, but chlorine is Gauss, so it has got a considerable dipole moment. But I will ask you, out of the 3, which one is more stable? Perhaps you will say this one is more stable, because the bulky phenyl, the steric strain relief is more pronounced than the relief of dipolar strain, where the other one you will find phenyl will come Gauss, chlorine will go anti. But that situation is less stable than phenyl being anti. So then make a 120 degree rotation to get another, let us always fix the front carbon intact and make a clockwise rotation, make the staggered format. Chlorine will come here, phenyl will go here, hydrogen. So that here, this is very unstable. Phenyl has come close, chlorine has also come close. So another 120 degree rotation, keeping the front one fixed. And then chlorine will come here, phenyl will go here and hydrogen will come here. Now here chlorine is opposite, but phenyl has gone close. These three are completely different forms. No one has same energy. If the energy are same, the same type of interaction, both Gauss, both anti, then you will say either they are identical or enantiomers. They are often they're enantiomers, as you found. But here the clear-cut case, there are three different rotamers with different energy values. Here phenyl, Gauss, chlorine, also Gauss. Here chlorine, anti, phenyl, Gauss. Here phenyl, anti, chlorine, Gauss. So this is supposing I say this is 2, this is 1 and 2, this is 3. So in stability order, what will be the thermodynamic stability order? Which one will be the most stable? Which one will be, then what is the order?
1 is greater than 3 is greater than 2.
1, then
3 then 2.
yes, 1, 2 ka 3, no, 1, 3 ka 2, precisely 1 greater than stability is 3, then 2. Why? I will write down before I explain that steric strain due to Gauss phenyl groups is more pronounced than the dipolar strain due to two Gauss chlorine atoms. Got it? Here, chlorine Gauss, that is less pronounced because phenyl steric strain is minimum. So here in 3, you find chlorine are opposite, but the bulky phenyl groups, the very bulky phenyl groups with 6 carbon atoms, their steric strain is more pronounced than 1 chlorine, although it has got some electrostatic charge, but that dipolar repulsion is less pronounced than the severe steric repulsion here that will make this, less stable than 2. Why 1 is more stable? Because in 2, this phenyl is coming close as well as chlorine is coming close. That is why it is the most unstable form. While 1, chlorine, in no case the dipole moment is 0. Unlike the mesoform, one of the rotamers where all are anti, then mu was 0. But here, none of the forms, none of the rotamers has mu is equal to 0. Hence, the average dipole moment of the active form, because it is a weighted average of all the conformers, rotamers or conformers. The average dipole moment of the active compound is 2.85 Dv than the mesocompound. Mesocompound, the presence of one more stable, more abundant rotamer 1, that makes the average less. Mesoform 1.27 Dv. Got it? Did you get a feel of why did I call, or why do I call it's a wedding ceremony? Do you get a feel of wedding? Are you mentally dancing or not? Miss Samini?
Yes, sir.
Zabardasti? Are you
No, sir.
mentally dancing? Yes, sir. Good. So, on one side we discussed configuration, mesoform and active form, their configurations. And on the other side, in each configuration, we are having 3 rotamers. That is the trick. 2 times more, 120 degree. In the first case, in the meso case, 2 and 3 became energetically identical, but they are enantiomers, no doubt. But in case of the active form, whether RR or SS, same. There are three distinctly different, having different interaction energy rotamers. And in the equilibrium mixture, you will find maybe say 60% of maybe 50% of one, and maybe 30% of maybe 60% of one, 30% of three, and the minimum say 20% of two, or maybe still less. 2 maybe 5%, who knows, but all are there. They're interconverting between themselves, but at a given point of time, one is more abundant, the least abundant is 2, and the intermediate abundant is 3. I think I will close today's session little premature before 2 hours to make myself available to a party, not a party. I always say party because whether it's due to the demise of a person or a birth of a person, same thing. It is a cyclic process. So I'm not happy to declare that the entire aspect of stereoisomerism is finished, because I will take some more examples. And of course, I declare that the public session will not be there anymore for stereoisomerism, and we will be sitting in our program. Maybe I shall upload them. Will do in a manner that it will be benefiting to those who are following. So you will be definitely getting lecture 8, but not live streamed. Enough is enough. So bye-bye.